Hi, this is problem 10 from the 2017 AIME. Let Z1 equal 18 plus 83i, Z2 18 plus 39i, Z3 78 plus 99i. Let Z be a unique complex number with the properties that this product is a real number and the imaginary part of Z is the greatest possible. Find the real part of Z. Oh boy, this looks complicated. Let me try to draw out these points on a graph to see if I understand where they're located. Hopefully I can do that without making too big of a mess. So I have my real and imaginary axes. So let me try to draw this out carefully. So we have Z1, or excuse me, Z2 located at 1839. Z1 is just above that at 83 and 18 on the real. We have Z3 located at 78 on the real axis and 99 on the imaginary axes. Okay, so that looks pretty clear. I noticed that this is a delta of 60, this is a delta of 60, so it looks like Z2 to Z3 lies along a 45-degree line, so that may be helpful later on. Now we have this fourth point Z that we have to place on this plot, and let me just put it somewhere up here just so I can sort of keep track of it. So let me put Z up here. And it looks like we're using these four complex numbers to form this product, and we want this product to be a real number. Now what I noticed from this product is the difference between various numbers of interest, and these differences in the complex plane are really just line segments. So we might be able to make a correspondence between this product and some sort of geometric interpretation, because I see that I can rewrite this a little bit differently, and I notice that Z3 minus Z1 times Z2 minus Z1 is equal to some real number, R, times Z3 minus Z over Z2 minus Z. So essentially, in terms of the angles of these complex numbers, we know that the angle of this expression has to equal the angle of this expression in the complex plane, because again, this is a real number. And we know that these differences are basically line segments in the complex plane. So let's see what these line segments look like. So Z3 minus Z1, that's just this line segment. Z2 minus Z1, that's this line segment. Now the angle of Z3 minus Z1 is essentially this angle right in here. Z2 minus Z1 is the negative of this angle. So the angle of this complex quotient here is just the angle, this angle minus the negative of this angle. So the angle of this expression, alpha, is just this total angle here, alpha. So that's pretty handy. And by a similar analysis, we can see that this expression on the right is just the angle beta, where beta is now defined as Z3 minus Z and Z2 minus Z. So really, this complex expression is just a roundabout way of saying that the angle alpha is equal to the angle beta. And what that tells us now is that these 4 points are all lying on the same circumscribed circle. So let's try to draw that in. So the circumscribed circle of those 4 points would look something like this. A little lopsided, but you get the idea. And now we're trying to find the z located on this circumscribed circle that has the maximum imaginary part. And so from geometry we see pretty clearly now that in order for z to lie on this circle and have the maximum imaginary component, it has to lie directly above the center of the circumscribed circle. So this now tells us the target value of the real part of z. The real part of z will be the real part of the circumscribed circle's center. So now it's a geometric problem of trying to find the circumscribed circle's center given these 4 points. So now let's talk about just the x-axis and the y-axis going forward, since we're just talking about a coordinate geometry problem. And the way we're going to find the center of this circumscribed circle is to look at the intersection of the 2 perpendicular bisectors. This looks like a pretty convenient chord to draw a perpendicular line segment because we just have to take the average of 83 and 39. That's just 61. So that tells us the y-coordinate of the center of the circumscribed circle. The other chord that's convenient is to use this chord from Z2 to Z3 because we know that that's a 45-degree line. We can calculate the center of that chord pretty simply to find out that that's coordinates 48, 69. The perpendicular bisector of this chord is also a 45-degree line. And the y-coordinate has to go from 69 to 61, so it has to drop down 8 units, and then the x-coordinate has to move over by 8 units because it's a 45-degree line, from which we then determine that the real part of the center of the circumscribed circle is 48 plus 8, or 56. And 56 is our final answer. Anyway, that's a bit of a roundabout solution. I think it's probably the best way to go. We could do a bash on trying to figure out the conditions and just using complex arithmetic, but I think that's probably a little more difficult. I think the geometric interpretation is probably the less error-prone of the 2 methods. So hopefully that helped, and we'll see you at the next video. Take care. Bye-bye.